first and foremost, if you see that you have a, not a 0, but like a 40 on your exam, please do not panic. That is literally just the auto-graded portion of your exam. That's a feature, not a bug. So that's just telling. So if you actually look at the details of your exam, you will see that there are plenty of answers or questions. You'll see that there's plenty of questions that still need to be graded, right? That's not going to happen tonight, simply because it's my birthday, so I'm not going to be grading tonight. Yay, thank you. Okay.
Also, one quick question. When you say it's a feature, not a bug, do you say that like it does not, or?
I say that like it's working, there's no errors, it's working as intended.
That's also what the test says.
But they lie. All right, I don't know how we keep getting more HDMI cables in here, but we do. So the sorting assignment, again, is basically three different sorting algorithms. Okay, so full canvas. Okay. Three different sorting algorithms. You've got to do insertion sort and quick sort, which are pretty important things. Now I want you to do an in-place quick sort as opposed to like splitting it up into subarrays and basically breaking an array into multiple arrays and splitting it up like that. I want it like in-place quick sort like I describe in my videos, as well as the way I describe that's described in the textbook and in the slides. So in other words, do it in place. Quick sort is one of quick sort's big appeals is that it's done in place. All right. Now that said, an interesting point about quick sort is that we can actually kind of look at how Java does sorting algorithms. So Java arrays sort. So if we look at the Java, sort thing over here, we'll see that if we take in an array of objects, it does one thing. And then if we take in an array of, let's see, where's quick sort? Okay, if we just take an array of integers, it will sort it using quick sort, a specific version of it called the dual pivots quick sort. You don't need to implement that. It's just interesting. It's just good to know that if you're dealing with primitives, you are going to be dealing with that quick sort is the default kind of way of doing things because primitives don't need to be kept stable. In other words, any one 5 is no different than any other 5, so it doesn't matter. Okay, and and because you're apparently using two pivots, that makes it faster and you don't get the worst case scenario as often. However, when you're sorting in general, you don't necessarily know if you're sorting, if things can't, you don't know if things have to be stable, which is that equal elements will not be reordered as the result of a sort. In other words, if you have a 5 of hearts and a 5 of clubs in your input, the 5 of hearts is going to come before the 5 of clubs in the output if the 5 of hearts was before the 5 of clubs in the input, right? It's going to be basically equal items will come out in the same order according to that. And that's important for some cases. So the idea here with the sorting out so the sorting algorithm used for basically any object is timsort, Tim Peters list sort for Python, timsort. And then here's the citation for it. And as you can see, it dates back to the 90s, which is a lot sooner than other sorting algorithms. All right. So you're implementing insertion sort, which is always good to know, quick sort, and then one of the following below, which is, and if you do timsort, because that's more complex, it's got 7 points of extra credit. Shell sort, however, is interesting because we do not know the optimal time complexity for it. It is still an unsolved problem in computer science. So if you're interested in unsolved problems in computer science, I highly recommend taking a look at shell sort because it is pretty unique in the way it operates. Its runtime is very unique. Otherwise, I would do merge sort or heap sort. Okay, so the idea here is that we want to modify, you want to modify the sorting algorithm to keep track of the number of comparisons performed, the number of exchanges performed, and the total runtime of the algorithm. Now, a comparison isn't always an if statement. An if statement isn't always a comparison. When we talk about comparison, we're checking, when I say comparison, I mean, we're asking, are these two items out of order? Or are we checking if one is bigger than the other? That's what a comparison is. We're checking if we're inbounds or out of bounds is not a comparison. An exchange is just simply when we swap two places or move something in memory. And runtime is fairly straightforward. So I mentioned to test this algorithm many different sizes of the list or arrays of integers. So you can do it, you can implement this, your sorting algorithms over lists or arrays. I don't really mind. But the idea here is that a decent test list might have sizes that are powers of 2. So let me go ahead and pull up the code. I wrote this in this morning's lecture to kind of express what I mean, and kind of just give you the basis. And I'll send this out as an announcement so that you can have access to it. Okay. So here, what I've done is that first off, I've got, let's start right over here with the generate array of numbers. That's the most, so ignore everything else. Just we're going to look at the generate array of numbers. So given the size of an array, we want the size of an array. We're going to make an array of that size. I do so by creating a new random object. Now, here's an interesting thing about random. Okay, and let me go ahead and comment out all this stuff for our main. The interesting thing about random, so let's call gen, and let's go with, we'll just create an array of 8 items. And we'll just add in a array sout arrays toString so that we can see what we're doing. Okay. So random is equal to new random. That creates our new random generator. We create a new empty array of that size. And then for every item in the array, we assign a random value. Straightforward stuff, nothing, right? I don't have anything, in my sleeves kind of stuff, no tricks, right? This is exactly what you would expect for just generating random numbers. So, and now I'm going to print it out, and I'm going to print out a size, something of size 8. Okay, assuming it runs at some point, I guess. There we go. It was just working on it. And there we go. There's a bunch of random integers. They're quite big, but that's randomness for you. If we wanted to, we could make a bound for these things. Like the bound, like I could put in 3,000 here so that nothing would be greater than 3,000, I think. Can't remember if it includes the bound or not. But as you can see here, it's generating random numbers. Right, and each time I press it, it's random. But one of the things but what if you don't want it to be completely random? What if you want it to be statistically random? Okay, statistically uniformly distributed, but you wanted your results to be reproducible. That's what a seed is for. So here I'm going to put in the combination to my luggage. 1, 2, 3, 4, 5. No Spaceball fans. And now with the seed, it's going to go ahead and every time I run it, it gives me the same randomly generated numbers each time. You can't really predict what numbers are going to come up. But basically, we're just simulating the same kind of stuff. We're starting the random simulation from the same starting point. So that's useful if you want reproducibility. Okay. So now that we've got this, For collecting data, there's a couple ways there's two big ways you can do it, okay? The first way is for individually for each time you run something, you have a static variable, right? A static variable for a number of comparisons and number of slots, and you increment those each time this happens. Those are useful because they exist outside the functions, and therefore you can, and therefore you don't have to really think about it with the way you're doing recursion, which can be nice. The other way to do that is to have your sorting out, your sort functions don't return anything in general because they are void functions and they affect the array they're operating on. So instead, what we can do is that we can make it return what I call a data object, which just simply contains the data that we're collecting. Specifically, it's just a very simple class. It's more like a C struct than anything else because it doesn't have any real functions. It just has a comparisons and exchanges, and that's it. You pass it, so if I wanted to sort an array, I'd do the sort, and then, I'd create a new data object. So I'd go data D is equal to new data, right? And then return D. And then as I do the sort, I update data. Like whenever I do a comparison, I might do D dot comparisons plus plus, right? And then I return this object. Does that make sense to everybody? So that way, that single data item is useful. Now, what if I'm dealing with recursion though? Right, I don't want to create a new data object for each sub tree. I mean, you could do it that way and like combine them. But the way I would do it with a recursive sort is I would, pass in the array you want sorted, create a data, and then call a secondary function that actually does the sorting and pass in the data. And because it's passed in as an argument and will be passed in as an argument to all the functions, to all the recursive calls, it's the same data that you're working with. Make sense? So here's kind of the way that I imagine this going. And let me go ahead and remove this outer loop first. Sorry, let me remove this inner loop for a second. Okay, the idea here is that, so 4 int 5 is less than or equal to 10. What am I doing there? Well, I'm doing what powers of 2 I want. So what I do, so this is how you might, run this for like insertion sort or something, which is that, hey, for every so for 5 to 10, create an array that is 2 to the 5th, then 2 to the 6th, then 2 to the 7th, then 2 to the 8th, then 2 to the 9th, and so on and so forth, that big, right? So create a number, so create one that's that big, it's randomized, then sort it, right? That makes sense? So here I'm gonna, so 2 to the 5th, that's 2, 4, 8, 16, 32. So that starts out at 32. Then we test one on 64, then one size 128, and so on and so forth, right? So the idea here is that we are checking basically the comparisons and runtimes for this to go on for each size, right? But because it's random, the data could be a bit swingy, So we might want to run that multiple times. But the idea here is that you get your data and then you can output it somehow, either be a print statement, which you then copy and paste into an Excel file, or you could just write a CSV file, manually, and the CSV file will automatically open in Excel. But what if you want to be a bit more thorough, which I would hope you would want to be. So here, what I do is I create a second for loop. And that for loop is an inner for loop. So what I do is I create a list of data called results. And this might be the list for insertion sort results, because I don't want to mix my results up, right? So for I is less than 10. So do this so create a random array 10 times and get the data from it. And then add that result to our result list. Make sense? And then once I've got all my results, I can compute the average for that size. Rather than having one, that way my data point is a bit more accurate. Okay, and it's less wobbly. Okay. So what you're gonna, and so now that once I get this data, the idea here is that what we want to do is that we want to essentially graph it in some way or make it easy to see. So for an insertion sort, again, if I open up whiteboard, I would expect to see a graph that looks something like this, which I've already drawn. Which is that, hey, I've got some n, okay, which is the size of the array. And then I've got some time. And if I connect the dots, I see that I get a quadratic fit to the dots, to the runtimes. And the marks on the axes aren't equal because guess what? Right? 2, 4, 8, 16, 32. It's going to be, but the idea here is that we see a clear, quadratic function is the idea with our graph. That makes sense to everybody? So it's not too, I'm not asking for something too scary here. So implementing them is worth 70 points in general. And then the remaining 30 points are for the implementation of collecting data and presenting it. So this one is fairly easy compared to other ones. The hardest part about it is understanding how to collect your data, which I've just kind of explained to you, which again, I'm going to now copy. Announcements. $21.68, sorting. Code from lecture. And I would like to also remind you, you do not have to work in Java for this, or for any of the homeworks remaining in the semester. I mean, your final exam will still be done in Java, but you're free to tackle these programs in Python or whatnot if you want to take the opportunity to learn another programming language. Or if you want to like prove once and for all that your programming language of choice is faster than the other programming languages and therefore those programming languages suck, then there's your opportunity to do so. I will remind everybody of Bjorn, I think it's Bjorn Strusup who said that there are only two types of languages. There are languages that people complain about and languages that nobody use. So, all right. So if you've got questions about the exam or you've got demos to do, I will take those now.